I need my pen. Okay. So let's see. I'm trying to switch to where just my video is. There we go. Okay. All right. So who do we have here? Colin, Julie, William is online. Austin, Sophie, It's Friday. It's good, right? I know, I'm so tired. I'm so done. Okay. Well, so what we've been working on is a couple things. I've got this handout here where we are talking about different kinds of rings. I need to prove a theorem that says basically what do you get for free when you try to prove something's a subring. Okay, so say you have a subset of a ring and we want to prove that that subset satisfies the ring properties. There are some properties we get for free. So there's a theorem about that. So we need to get that done today. But I just don't feel like y'all are in a place to do a whole lot today. Is that true? I kind of think so. So, and then some of you all, I had extensions on the homework. So I know some of you may have some questions or something on homework. So let's do class for like 20 minutes. And then if you want to hang around and ask questions on homework 16, you're welcome to do that. Does that sound good? Okay, let's try that. All right. So where are we on this worksheet here? We had gone over, we were looking at number 5 here. Which of these algebraic rules do you think apply in the following cases, and what are some interesting sets we could test? So we were spending time talking about, we had talked about the real numbers, integers, rational numbers. We were talking about the odd and even numbers at the end of class last time. We said the odd integers are not closed under addition, okay? And so they are not going to be a ring. We didn't quite have time to talk about the even integers, but let's start there, okay? So we're going to talk a little bit about the even integers, then we'll talk about Z mod n and so on. Okay, so for the even integers, what are some properties that you in your groups, if you can remember what you talked about on Wednesday, had said the even integers satisfy? So we're looking at these ring. So are the even integers closed under addition? Yeah. They're associative. It's just regular old addition and subtraction on the integer, addition and multiplication on the integer. So we're going to get associative, commutative, addition, commutative addition. Yes. Additive, zero element, additive identity. Yeah. Now, if I think about what is the additive identity in the even integers, what? Zero, right? And we had talked before, remember a long time ago when we were defining even and odd, we were talking about is zero even or odd, you know? And we were coming up that a 0 satisfies that it's 2 times some integer, right? So 0 is actually even. And so what the odd integers would not have 0, right? So the odd integers, not only do they not have closure for addition, but they also do not have an additive identity element, because 0 is not odd, it's even, right? So we can put that on the odd integers. What about additive inverses? Does the even integers have additive inverses? You need negatives, right? So we have negatives in there. So we have additive inverses, okay? What about closure for multiplication in the evens? If you multiply an even times an even, does it stay even? Yep, it's closed under multiplication. How about associative multiplication? Yes, because we get that for free because it's integers. The integers have that. And distributive laws are going to work. Yep, we're going to get those for free. Okay. What about the other things? It's commutative. Multiplication is commutative in the even integers. What about identity? Do the even integers have a multiplicative identity? No, because our multiplicative identity for the integers is what? Is 1, and 1 is not even. So the even integers do not have a multiplicative identity. So they are a commutative ring, but not with identity, right? And then for field, it has to have, okay, well, is it an integral domain? Does it have 0 divisors, the even integers? Could you multiply 2 even integers and get 0? No, they're integers, right? We're still talking about multiplication and addition in integers. So we don't have 0 divisors. So it is an integral domain. Is it a field? Does it have multiplicative inverses, the even integers? To have multiplicative inverses, we need fractions, right? We don't have fractions in the even. So it is not a field, okay? So it is a ring. It is commutative, does not have identity. It is an integral domain, but it's not a field, right? So we've got all of those things going on. What about Z mod n? What about Z mod n? Okay, so in Z mod n, does it have closure for addition? Yeah, so we can add things in Z mod n. Now, we've done a lot with Z mod n, so hopefully you feel comfortable doing addition and multiplication in Z mod n. It is closed under addition. Associative, yep, we're gonna have that. Commutative, yep. Additive identity. Z mod n have an additive identity? What is the additive identity in Z mod n? 0? 0, the additive identity, or n, yep. So the congruence class of 0, which would also include n. Yep. Does it have an additive inverse? Z mod n, additive inverses. Remember our addition tables? We definitely had additive inverses. Now I want you to think about your multiplication tables in Z mod n. Okay, what do we have? Do we have closure for multiplication in Z mod n? Did you ever multiply things in your multiplication tables and get outside the ring? Nope, it's closed under multiplication. Associativity, yep, because the thing about Z mod n is it's building off the structure of Z, right? Because when you multiply 2 congruence classes, you can use theorem 2.3 to break it down to where we're just multiplying integers really, and then going back to modding out. Yeah, so we're gonna have some of those things we're gonna get for free because multiplication in Z mod n is related to multiplication in Z, right? So, so we get associativity, we get distributive laws. So Z mod n is a ring. It is a ring. It's going to satisfy all of those things for a ring. Okay. Is it commutative in Z mod n? Is it commutative? Now think about your multiplication tables in Z mod n, right? If I did like 3 times 4 in Z mod 6, would that be equal to 4 times 3 in Z mod 6? Yeah. And we noticed something about the structure and the patterns in the tables that showed us it was commutative. What did we notice? Do you remember in the multiplication tables? We had these multiplication tables. Let's say we're doing like Z mod. I'm going to do Z mod 4 because I don't want to make a big huge one. But in our multiplication tables, we'd have 0, 1, 2, 3, right? And what you'll notice is, so this is multiplication, so we'll have 0, 0. And we'll have 1, 2, 3, 1, 2, 1, 2, 3, 2 times 2 in Z mod 4 is 0. 3 times 3 is 9, which is 1. 2 times 3 is 6, which is 2. So we get that. And so it is commutative because why? I can see this diagonal. It's like symmetric. Like it's has this symmetry about this diagonal. And that symmetry in the multiplication table is telling me that it's commutative. Okay, so that's what we're seeing there. Okay. So it is commutative ring. So Z mod n is a commutative ring. Okay, does it have identity? Does it have a multiplicative identity element? Yes. We want to look for this in our table. We want to look for an element where this row matches that, right? That's my additive identity element in my table. Okay, so you can see it. So 1 is our additive, sorry, golly. Yeah, I'm in the same boat as y'all. Well, it's our multiplicative identity. 1 is our multiplicative identity. So it is a ring with identity. Okay, so is it an integral domain? So to be an integral domain, you need no zero divisors. Is Z mod n an integral domain? Benjamin went like this. What do you mean?
Sometimes it is, sometimes it isn't.
Sometimes it is, sometimes it isn't. When is it an integral domain?
When it has zero, so when it's prime.
When it's prime, yeah. So in general, Z mod n is not an integral domain. But Z mod p is an integral domain for p prime, right? Z mod p will be an integral domain. It won't have any zero divisors. So in Z mod p, we can do all these algebraic things that we can do in Z because I have multiplicative inverses. So I can solve equations in Z mod p in the same way that I solved them in Z mod n because I don't have to worry about zero divisors. Okay, so that's kind of a nice thing about this. So Z mod p is also a commutative ring with identity. Right? And are these guys a field? So to be a field, you have to have multiplicative inverses. Does Z mod n have multiplicative inverses for every element? Not always. Yeah, so this is not a field. What about Z mod p? Does it have multiplicative inverses for every non-zero element? Yeah, so this one is a field. That one is a field. Okay, so Z mod n and Z mod p. So we kind of went through what they were doing. What about polynomials with real coefficients? Okay, so polynomials, it's going to end up being a ring. So it's going to satisfy all of those conditions. So we're going to have closure for addition. You add a polynomial to a polynomial, you get another polynomial, right? It's going to have associativity. It's going to have commutativity. If we're talking about adding polynomials breaks down to adding real numbers, right? So it's the same type of addition. The addition doesn't change too much. So we're going to have commutative addition. Do we have an additive identity element in Z mod p or in the polynomial ring? It's just 0. So, but we think about 0 not as a number, but 0 as a function, right? As a polynomial. So it would be 0, but that 0 is not just a number, it's actually a function, the constant function at 0. So it would be this function. Okay. So this we can think of as a polynomial, some p of x equals 0. And it's just this constant function at 0. That is our additive identity element. When I add that polynomial to any other polynomial, it remains unchanged, right? What's our multiplicative identity element in the ring of polynomials?
1.
It's going to be 1. Yeah, it's going to be 1. But again, it's going to be the function, the constant function 1, right? So it's going to be actually this function here. That's the constant function 1. So that's my multiplicative identity in the ring of polynomials. Okay. Do we have additive inverses in the polynomial ring? Yeah, I can just say the additive inverse will just be the negative of a polynomial, will be its additive inverse. So I have that. Do I have closure for multiplication? If I multiply a polynomial by another polynomial, do I get another polynomial? Yeah. So if I multiply polynomials, I get a polynomial. It's closed under multiplication. Associativity will have in that set, and then distributive laws we'll have. So it is a ring. So the polynomials with real coefficients are a ring. They're going to satisfy all those things. Let's look at the other conditions. Are polynomials, is multiplication of polynomials commutative? Can I multiply polynomials in any order and end up with the same thing? Yep. So it is a commutative ring. Does it have multiplicative identity? Yes, we talked about that. So it's a commutative ring with identity. Is it an integral domain? We talked about that in length on Wednesday. It is an integral domain. Is it a field? Do we have multiplicative inverses in the polynomial ring? That's things like fractions. Ooh. Well, we would have to have 1 over a polynomial. So those kinds of things are not polynomials anymore. Okay. So it's an integral domain. It's a ring with identity. It's commutative, but it is not a field. We don't have multiplicative inverses in the polynomial ring. Okay. So I can write that all out. Are you writing on your paper? Maybe you're not. So we have the polynomial ring. Okay. So what's the notation for the polynomial ring? I kind of forget what the notation is for that. So I'm just gonna write it out in words. So for polynomials with real coefficients, it is a commutative ring. It has identity. It is an integral domain. But it is not a field. Yeah, not a field. Okay. What else do we have here? 2 by 2 matrices with real entries. So if we have 2 by 2 matrices, so let's think about matrix addition and matrix multiplication are my operations I'm dealing with here. Okay. Matrix addition and matrix multiplication. Okay, let's go through everything. Can I add 2 matrices, two 2 by 2 matrices and end up with another 2 by 2 matrix? Yes, it's closed for addition. Is it associative? It's going to be associative because when you add, you end up adding the elements, corresponding elements. And then once you're inside of those elements, it's just adding real numbers. So you get the commutativity from the real numbers and it's gonna carry over into commutativity, or sorry, associativity there and commutativity. Is there an additive identity element in the 2 by 2 matrices? Yeah, what's the additive identity element? The 0 matrix, so 0, 0, 0, 0. So that matrix will be my additive identity. Is it closed under multiplication? Can I multiply a 2 by 2 matrix by another 2 by 2 matrix and end up with a 2 by 2 matrix? Yes. So it's closed under multiplication, and we'll get associativity and distributivity because multiplication and addition for those are end up breaking down into multiplication, addition, and the real numbers. So we're going to get that. So 2 by 2 matrices with real entries, it is a ring. It's going to satisfy all of those conditions. Okay. Is it commutative? Is multiplication, matrix multiplication commutative? Can I multiply in any order? It's not. So hopefully you've all had linear algebra and you remember that is not a commutative operation. Okay. So it is not a commutative ring. Does it have identity? Do we have a multiplicative identity element? What is it, Krista?
The identity matrix.
The identity matrix. There you go. So it's 0, 1, 1, 0. And so when we called that the identity matrix, we really assumed we meant multiplicative identity, right? And so sometimes in mathematics, we're a little bit loose with our terminology there. I would say that's one time we're being a little loose because it is the multiplicative identity matrix, right? And we have an additive identity matrix also, right? Which is the 0 matrix. Okay. So, so yeah, so it does have identity, multiplicative identity. Is it an integral domain? Can I multiply 2 matrices together and get the zero matrix when those two are non-zero? I did an example in class on Wednesday, didn't I? I came up with a counterexample on that. So I don't remember what it was. It had a bunch of zeros and a couple of ones. Was it this? I think the one had to be. That was, I mean, you could do other ones, like you could put the one in different places or whatever. But this guy ends up multiplying to give me 0, but these guys are non-zero. So you can have some non-zero things multiplying to give you 0. So it's not an integral domain. So all you need to prove it's not an integral domain is to find one example. Proving it is an integral domain is harder because you have to show it in general. But it's not an integral domain, and there's my little counterexample on that. Oh, sorry, William. There it is. Okay. All right. So, sorry, I feel like I'm just talking a million miles an hour. Are you guys good? We good on this? Yeah.
So, how you said it's a commutative ring, but how is that different than associative multiplication?
Commutativity.
So different.
Yeah. So, oh, I see. Yeah. So commutativity is left off of the list for multiplication because it's not always satisfied for every ring, you know? So commutativity is that you can multiply in any order, and associativity has to do with parentheses grouping.
Okay.
Did that help?
Yeah.
Sort of, maybe. Okay. And so I was talking with Dr. Ortman about this, and I told him, like, I showed you all an example of when an operation is not commutative. It was like the x to the y thing, you know, it's not a commutative or it's not associative. And so then he was like, oh yeah, my class came up with another example that's not associative, and it was cross products. So if you do a cross product, if you do like B cross U and then cross W, it's not necessarily equal to B cross U cross W. So cross products in Calc 3 ends up being not associative also. So here's another example of something that's not associative. This is kind of like a product, right? But yeah.
It says that an integral domain has to be commutative. And we said it's not commutative. So
What's not commutative?
the matrices,
The matrices is not commutative.
that's what we said, I'm pretty sure.
Yeah, and so it's not an integral domain.
Yeah.
Oh, I see what you're saying. Oh, that's a nice counterexample. Very good.
Because it says that AB equals 0, then A equals 0 or B equals 0, and we came up with something where neither of them are 0. So that means it's not a domain.
It's not an integral domain.
Yeah.
And you're saying it's also not commutative for that same reason?
Well, I'm just saying we already said it was not commutative, so it can't be an integral domain.
Oh, yeah. Oh, that's good. Okay, yeah. Okay, so that's a nice way, because I was just saying, like, it's kind of hard to show something's not an integral domain, but if it's not commutative, then it's not an integral domain because the integral domain has to be a commutative ring. Thank you for pointing that out. Yeah, that's really nice. That saves us from having to try to prove that you don't have two things that multiply to 0, right? Because you can just throw it out with commutativity. Good. Is it a field? 2 by 2 matrices multiply together? Do we have multiplicative inverses for every matrix? Jake, what do you think? You're like, I thought you were raising your hand. Yeah, okay. Yeah, so if you remember in linear algebra, you talked about whether or not a matrix was invertible. Remember talking about that? And not every matrix is invertible, right? So in other words, if it has like this one would not be invertible because it has a 0 row. If it has any 0 rows or 0 columns, or if it can be row reduced to something that has 0 rows and 0 columns, it's not invertible, right? And so, so if we're just talking about matrices, 2 by 2 matrices, all of them, then it does not have multiplicative inverses. But we could restrict it to the group of all the ones that do have inverses. So that's called the general linear group. And that is the 2 by 2 matrices that have inverses. So you could do a subset of the matrices that has multiplicative inverses and talk about that. And we do that sometimes. So anyway, okay, so that's I just wanted to kind of go through, I wanted to do that theorem today, but we're gonna stop because I think we're good. This today, y'all are tired, and some of you still need to finish up homework 16. And so, so we'll just take a little bit of time to breathe and do that, and we'll do that last theorem. Well, it's gonna have to be Friday, because Monday and Wednesday, we're gonna be taking that exam, okay?
Monday we're doing review questions and then.
Well, so Monday we'll do some review time and then the memory work. Of course, last time I got here and y'all were like, we just want to do it. So I don't know how you're gonna feel on Monday. Do you want to do like the first 30 minutes of class, do your memory work, and then you can hang around for questions after that? Would that be a helpful way to do that? That way it kind of satisfies both things. Okay, so let's do that. So we'll just have 30 minutes at the beginning of class to do your memory stuff. And so that'll be some definitions and then proving some of the theorems. So I gave you I think a handful of theorems that I wanted you to know the proofs to. So it was theorem 1.7, which is proving that every integer can be written as a product of primes. And then it was theorem 2.1, which was essentially showing that congruence mod n is an equivalence relation. Okay, so I want you to know the statements and proofs of those theorems. And then the other one was theorem 2.8, which that's the one that was the following are equivalent. Now that's a long one, so I wouldn't ask you to do that whole proof, right? But maybe a piece of it. Okay, yeah, Zach.
Sorry, I kind of missed it. Did you say 1.7 and 2.1?
1.7, 2.1, and 2.8. Yeah, so those are the ones I want you to study for Monday. And then I won't ask you to do all three of them. I won't ask you to do all of 2.8 because it's too long, but know the statements and proofs of those theorems and then the definitions for Monday. And then for Wednesday, we'll have some more proofs that are homework level proofs. And then, and since there was a lot of computation on the homework, I will have a problem that has some computational stuff. Okay, so that's that chapter about Z mod n. We did a lot of computations in that chapter. So, so things like, multiplication tables and things like solving equations and things like finding zero divisors and units and things like that.
And for the solving equation, just showing your work, just showing that you tried.
Sometimes, yeah. Mm-hmm. Yep. Yes.
On the memory portion, I mean, obviously we need to know the statements and the how to use all of the stuff, the theorems that we learned, but do we need to like memorize them by heart, those 18 theorems, to know the statements exactly?
Not really. I mean, yeah, like, and you don't need to know the number either. So I would say do your best on that because you're going to need to be able to use them, right? So you're going to need to be able to use the statements. So if you don't know what the statements are, you can't use them very well. So,
Yeah.
yes. Yeah.
Okay.
Mhm. Yeah. Okay. Other questions about the exam, Kathleen?
Oh, sorry, well,
Oh, okay. Well, whatever.
can you said it for a second, I didn't really catch what was going on. We said something about multiplication being commutative is related to integral domain. I wasn't quite getting it.
Oh, yeah, that's fine. So in the definition of an integral domain and a field. So to be an integral domain or a field, you have to first of all be commutative. And so what Callista was pointing out is that the 2x2 matrices are not commutative. So there's not even a chance they could be an integral domain or a field. So that's what she was pointing out.
So do we have so I guess my question would be, is that just a convention thing for making it nicer, or is there a name for when it's not commutative, but it is an integral domain, or it's like when it's not commutative?
So you're saying, is it possible for something to have zero divisors and be non-commutative? That's what you would need to have in order for it to be a thing, right?
Or I think it does not have zero divisors, but it's also not.
It's just a regular ring, maybe.
Okay.
So I think, yes, I think what you're saying, well, maybe I don't understand what you're saying, but, or maybe you're not clear in your head either.
Yeah. It sounded like a second ago she was reading something, I think, out of the text, and it sounded like it was saying that I guess I didn't understand if it was like a by definition thing, or if it was, there is a theory thing, but it was like,
Yeah, and it may be, like, I don't know. So to figure out if it's a theory thing, we would need to answer the question. Is it possible to be non-commutative and also not have zero divisors, which is, I think that's what you just said. Yeah, so is that possible? And so the question is, I don't know off the top of my head. I have to think about it. So, so Z mod 4, for example, has zero divisors and it is commutative, right? With multiplication, but it's just a ring. So I don't know, maybe we need some more time to talk about this, but maybe we'll do it another time. Yeah. Okay, other thoughts, questions? Yes.
In regards to the theorems,
Mhm.
hypothetically, if it was like a test question, would you say like write theorem 2.6?
You could, if you wanted, if you know that that's the number for it, or you could just say by a theorem.
Okay, if it was something we had to, like, for the memory board, would you write as the question on the test? Like, write this theorem? Like,
Yeah.
write the-
Yeah. So, so in the, I have kind of like little parenthetical descriptions of the theorems, right? And I would say something like prove theorem, blah, blah, blah. That's the one that says da, 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 you know, and then you'd write out the formal statement. Does that make sense? Yeah. So I give you like a hint of like, it's this one. It's the one that does that. You know, theorem 2.3. Oh, that's the one that allows us to go back and forth between mod n and the, you know, the bracket notation and the regular Z, you know. So, so things like that. Does that help? Okay, so let's stop. And then if you want to stick around and ask questions about homework 16, which was due last night, actually, you can do that. Okay. Have a good weekend. I guess I'll keep recording. That's all. Okay, who has questions on homework 16?
But I kept, like, pretty much on every single one, I kept running into the issue of like, I know exactly what this is saying, I know exactly why it's true, I just don't know how to write it in a proof.
Right? Okay, yeah. I think
Like, I could look at every.
that might be a description of like this whole course.
Yeah.
Right?
I can look at like every single multiplication table and it would make perfect sense, and I'd be like, oh yeah, obviously it. The way I was thinking about it was like, for the one, if it was a, if it had zero divisors, there's literally not room on the multiplication table to have every element. If you have a zero.
Because it repeats.
Because it repeats.
Yeah.
But I don't know how to say like, I don't know, it felt very hand wavy to be like, oh, just because it repeats, and I didn't know how to phrase that like
Yeah.
smartly.
Well, so in a lot of times when you're trying to prove something, you can get some traction by using theorems or definitions, right? So let's think back. What is the definition of a zero divisor? What is the definition of a unit?
I
Right?
couldn't find the definition of a zero divisor.
Oh, okay.
In the text. That
Okay.
was the problem I kept running into.
Oh, yeah. Okay, because
I
you need a
don't-
definition or you're gonna be sunk, right?
Yeah.
So
Well, what chapter is it
it'd be in section 2.3.
in?
It's like right.
It's at the end, and it's
It's just like
Oh, yeah, it's not in like a little definition.
it's not in a little box. No, it's not.
And so I didn't know how to use that definition really.
Okay, so let's say, okay, so we'll say this, an element A, so here's the definition. And I'll write it in brackets, the book doesn't. Because the book was being lazy, which I totally understand. A in Z mod n is called a unit. Okay, and so Yeah, so how do we show something is a unit? Well, I've got to find the X that makes this true, and then it's a unit.
And then what about for zero divisors? Is it the same thing but equal to 0?
Yeah, okay,
Okay.
so, well, hang on, so let's write it, we can write it out. Definition of zero divisor. So a non-zero element A of n. Of Z mod n. Is called a zero divisor. If the equation A x equals 0 has a non-zero solution. And so, so then we had some theorems that were showing that, well, we were showing things like, and we were proving things like, you know, the way you were thinking about these units and zero divisors is you were thinking about, is that number A relatively prime with n? If so, it's a unit, but that wasn't the definition. So so we kind of went back and forth with that, like we were proving things like that in our homework, right? And then same thing here, if A and N if the GCD is non-zero, then we end up getting this zero divisor thing, but that's not the definition. So that's something that we need to prove, right? And we were doing that kind of thing on our homework.
Okay. And then, so for like proving that if they're co-prime, we could use, there's a theorem in there that's like, if an element is a unit, then its GCD is 1. That's one of the theorems in the book.
Okay,
And then you
it's,
can,
which theorem is that?
I think it's either 2.10 or 2.9.
Okay. Yes, 2.10. Or, yeah.
And can we say like,
And we can prove it. Right? Because how? Well, if you have the GCD is 1, then you can write that GCD as a linear combination. Right? So you have that linear combination. And so then from that linear combination, you can rearrange things and show that and you can find what the solution is to that equation, right? So. Yeah, Colin?
So I agree this homework is really tricky. Something I ran into a bunch of times is, those are the definitions in the book. They don't set their definitions, but they don't use if and only if.
yeah.
And
did
I
wonder about
genuinely could not convince, like,
Okay,
it seems like it's.
okay, let's do this.
that. No, that was actually something I was thinking about, because I was like, I feel like this would be really easy to prove if I could use this definition backwards.
Yeah.
But I
Yeah,
couldn't.
I just used it backwards.
Yeah, it is an if and only if.
Oh, seriously?
Yeah.
Cause it feels intuitively, it feels like it should be if and only if, but like I tried and I could not actually like convince myself that it was
Yeah,
like algebraically. So it is an if and only?
it is an if.
Yeah, I struggled with it, but I didn't see another way. So like one of them I used 1 in place of AX.
Yeah, yeah, so a definition should always be an if and only if.
So I guess my only question is, we're like, when we do definition having an if and only if, it's just because we're like applying a name to something.
We're just naming it, yes.
If, sorry, so.
It sounds like homework
so-
16 is not gonna be very
So
fun.
the only
right?
thing, I guess the only thing that would have made me second guess is, at any point, would we ever come up with something else that we would also like to categorize as a unit that might not necessarily?
No, that's.
dang it.
Is there, I mean, this is in the homework, like kind of directly, but like, I don't know how to prove that something, so to prove something is a zero divisor, we have to take what we have and put it in the form of AX equals 0.
We have to find the X.
We have to find
that makes-
an
yeah.
X or like any X.
NEX, I guess,
Okay.
annex. I mean, if you know exactly what ring you're in or what mod in you're in, I mean, you could just
Oh,
write
yeah,
it down
you
and
can just do
find it. But if you need to do it in general, then you probably have to use other theorems that we have, things like linear combination or whatever, or that, GCD as a linear, you use that GCD as a linear combination like all the time. So that's one of your big tools that you have. Did you have a
Does-
specific one you wanted to look at, or?
I didn't know how to prove that something was a zero divisor.
Okay,
That was just like, what it was it was the one that was the AX equals B has no solutions.
I see what you're looking at.
Yeah, it's the 2.3.16.
Okay,
If A is not zero and B are,
okay, so tell it to me, read it out to me so I can write it down.
if A is not zero and B are elements of Zn. And AX equals B has no solutions in Zn.
I realized I didn't go back and finish that one over.
Prove that A is a zero divisor.
Okay. So proof. So we're just gonna assume all the stuff, right? We're gonna assume that A is not equal to 0 and A x equals B has no solutions. In Z mod. Okay. So what does that mean? So that means that if that has no solutions, then that means that AX is not congruent to B mod N for any X in Z mod N, right?
That was a jump, or that step was something that I did not know.
Oh, well, I mean, I'm just going off of congruent, like, what does it mean for two congruent classes to be equal? Right? So I'm just using that definition.
Oh, for some reason I didn't put together that like elements of Zn were congruent classes.
Mm-hmm.
And so I never made the association with any of the stuff.
Yeah, and so that's what we're doing over and over again. We're taking theorem 2.3 and using it backwards and forwards, right? And so we can take something that's in this congruence class notation and flip it over to the mod notation and do some things, then flip it back, or vice versa. We have it in the mod notation, you can flip it to congruence class notation and back and forth, right? And then that allows us to say some things. So now what do we get?
So I feel like, what we have is an inequality or incongruent,
I know,
and I feel like those are always hard to like.
it's a
directly
little bit
prove stuff.
hard,
So
yeah.
I don't know if my proof was right, but I started with assume by way of contradiction.
Yeah, so we could assume by way of contradiction or assume. Okay, so what's the logic here? Okay. So we have this condition implies that A is 0. So we could say assume all this and assume by way of contradiction that A is not a field divisor, or that A is a. Do we have that if A is a, I don't think we have yet that if A is. Yeah, okay. Because if it's not a zero divisor, it's a unit, but I don't know that we have that to use really here.
I think that's later in the.
Yeah.
That's a little
I think
later.
that's actually-
Yeah, that's another homework problem. Let me peek at my own solution to this because I don't remember what I did here.
Did you also feel like the questions are in the hardest order?
That's funny.
In exactly the reverse order, they would just like.
Flow better?
On each other.
Yeah, I mean, they're all like saying similar things. And so it's kind of, where is my solution number 16? I wrote all that out. Where is it? Yeah. Yes. Oh, you think so? Okay. What does it say? Yeah, I wrote out all the solutions to this homework and now I've lost it. Maybe someone stole it. I don't know. I'm just kidding. I don't think anyone stole it. Now I may have to redo that so I can grade. Okay, all right, what'd you get? Homework, theorem 2.8? What is it, or what does it say here? Okay, what part of theorem 2.8?
2.8 says, 3 statements are logically equivalent, that the modulus is prime, that if an element is not 0, then AX equals 1 has a solution. And if you have,
Yeah, but we don't have a prime, I mean, it's not Z mod P, it's Z mod N, isn't it, in this one?
yeah,
Or was there a portion of the proof that was useful?
I think it was a portion of the, or I think it was statement 2,
Mhm.
says A is non-zero, but we know the equation AX equals 1 doesn't have a solution. So would N be prime in this case?
No, I don't think so.
It does say, it does tell you that you, like, just below that proof, that you can use a similar strategy for Z mod N that says, translate Z mod N into equivalent congruence statements in Z, and then use the properties of congruence and arithmetic in Z can be used, and then the bracket notations for elements Z and may be necessary to avoid confusion. But then,
So, well, can we just keep
Yeah.
going with what we had here?
Yeah.
And I feel like we are, so what does this say? This says that AX is not, AX minus B
is not
is
equal.
not congruent to any, NK,
Is it not congruent or is not equal?
is not equal to NK or any K and Z. Okay, and so what does that tell us? We want to, yeah, we think,
so is it okay if I say what I did here? Just
Yeah,
in
I
case.
guess so.
I don't know for sure if it's right.
so you were saying you were trying to do by contradiction, which is reasonable when you
Yeah,
have
'cause I
this
want
not
to get out of the
equal.
inequality. So I said, assume by way of contradiction that the greatest common divisor of A and N is 1.
Okay, and then you're gonna get a contradiction, and that's gonna tell you that the GCD is not,
We'll
no.
eventually get, like, if you assume the greatest common divisor of them is 1, then you can eventually, I don't think it's that one, but eventually you get to the AX congruent to B mod N has a solution.
Yes, and then you can say, therefore, the GCD is greater than 1, and then from that you can get zero divisor.
Yeah, because you get some integer K where you get your AX minus.
Okay. Yeah, so that's an interesting logical structure that you did there, because the way of contradiction that you did was not that it wasn't the negation of this, it was like some other statement. You know? But I think it works. You can assume by way of contradiction that some other thing, and then you're essentially proving that if this is true, then the thing that you said, opposite of the thing you said is true.
Right.
And then you go from that to this.
Yeah, and which actually maybe that means there's a way to shorten the proof I did, but
Maybe, I don't know.
The first attempt I did at this, I went through it all the way, and I just ended up proving that if it has solutions, then it's not a zero divisor. And then I was like, "What? That's not. Is that useful, or is that?"
Okay, so that's the contrapositive of the statement.
Because I did a big
Yeah.
one
So
on the
you can
whiteboard,
assume-
but then I was
okay.
like, I don't think this
So-
actually proves anything.
So
I'm
the
gonna try it again.
contrapositive, okay, so if you have a statement, P implies Q. How much time do we have? We got just a little bit. P implies Q. The contrapositive is logically equivalent to that. And the contrapositive is not Q implies not P. And this might be a nice time to use the contrapositive. So we're gonna assume not Q. So we can
It
assume
has solutions.
that it's not a zero divisor. And then show that that thing has a solution. So this would be the proof by contrapositive, which I haven't really talked about.
I just feel like that makes the
Yeah.
most logical sense for this, because like
Yeah.
even like saying
Okay, so we're gonna assume that A is not a zero divisor. Is that what you were saying?
Mhm. I think I did it.
And we're gonna say, and then the last line will be thus, we have that AX equals B has a solution. Right, and so we've gone from not Q implies not P, and then we can say thus, the statement is proved.
Can you do not P into not Q to have it be correct, or is that, would that not work? You have to go backwards.
Yeah, you have to go backwards. So if you did not P implies not Q, that would be the backwards direction of this theorem.
Okay.
Right?
Yeah.
Yeah, and so that's why on one of the homeworks, it was an if and only if, and then people were proving things by contrapositive, and I was going, okay. I think it was you. I think it might have been one of the ones you were doing, because it was an if and only if, and you showed like not this implies not that. And I was like, okay, that's the backwards direction by contrapositive. And then I was like, and then you're trying to go forward. And I was like, I just got all confused. I'm like, which direction are we going?
On this homework?
No, it was on a previous one. I think it was on homework 11.
Is that,
So,
is that
and it may
still,
not have been you, but
is that still right to do though? If you're consistent about it, have you still shown both directions by doing that?
you haven't shown, you could show both directions by contrapositive, but yeah, it would be really confusing. But it's possible, sure.
I'm sad that that actually can work, because I wrote that all up on a whiteboard and then I was like, I don't even think I'm proving what I'm trying to prove, so I started over and I did had a completely different.
Yeah,
answer
so
that
if you
was
can
way
go
more
from here
incorrect.
to here, then you proved it and you proved the contrapositive of the statement, which is equivalent to the statement. Yeah. Well, I think it's time we need to go. But what were you gonna?
Well, I was just gonna say, I think that idea also makes sense to me, because if you assume it's not a zero divisor, I think you're a few steps away from showing that GCD is not, or the GCD of A and N
It's
is
one.
one.
Mhm.
Yeah. And then,
And then you can get the solution.
Yeah. which again, this might actually be shorter because
Maybe, yeah, I don't know. Yeah, I don't even know what I did because I lost my dumb paper, so. Who knows, it's probably in one of my offices somewhere. Okay, all right, well, I
Can I
hope that was
resubmit
helpful.
this?
Huh?
Can I resubmit? this
Yeah,
homework?
you
Because
can. I'm not grading this today. I'm not.
I did.
I'm not gonna grade it today. I really won't grade it tomorrow either, so.
all of my proofs were just word vomit of me trying to write as much of my logic through.
Right, right, well,
It's like,
and-
it's one of those things where it's like, it's so easy to look at a multiplication table and be like, all of this makes sense.
yeah,
And then it's like, how do I say this with like proper
Well-
terms? And then I tried to use like theorems and I kept just kind of going in circles and I was like,
Mm.
it's 11:59, I need to turn this in.
So I'm gonna tell you that I want you to have it done by like Saturday or Sunday, because on Monday I wanna post. I probably won't be able to, I don't know if I'll be able to have time to grade everything before the exam, like, or in time, you know?
Mhm.
And so I'll hopefully find or redo my solutions and post those on Monday.
Okay.
So I want you to have it done before then, because
Sounds good.
I don't want you to, yeah, once solutions are posted, it's over, you know, so. All right.
Have a good weekend.
Yeah, y'all too. Oh, Brandon,